In this quick set of slides, we're going to be talking about embedded energy and water. And in the lab, you did water and energy audits, measured your direct consumption. But as we know from the lecture material on embedded, there's really a lot more water used outside of your individual use. So there's all the other sectors, and for any particular product, there's the water or energy that's embedded, meaning incidental to creating that product. So this idea of direct consumption, you're familiar with it, and the idea of embedded energy or water. We talked about the water it took to grow the cotton, or for a towel and the lifetime of the towel, and what's the embedded use per month. So you can look at that. We did the same sort of exercise in class talking about diapers. So your audits were estimates of direct consumptions, and what would you have to do to improve those estimates? And asking this sort of question is what we do in environmental accounting. So here's just some other examples to think about, the diaper use presented in class. But let's look at another one, raised bed gardening. We talked about the amount of water it takes to water the plants, but what about the water it took to make the boards or mine the gravel in the raised beds? Maybe those are inconsequential, but maybe they aren't. And then we talked about beer again, the amount of water it takes to grow the grain and process the beer, and it takes about 1,000 liters to make 1 full liter of beer. So again, the question is, how would you improve your estimates of the total water? And this means you're going to have to start accounting for these other uses of water. So in class, we talked about energy efficiency of different houses. But when in the lab, you talk to the direct energy and the efficiency of the Provetcho stove, or the StoveTech stove, or the propane stove. But how much energy did it take to actually make that stove, or make that propane stove, or store the propane in the canister? And the other question you want to ask is durability. You saw the wood gas stove is a very lightweight, sort of simply built machine, but it could get crushed easily or might have a short lifetime. So the durability of, say, the StoveTech, the metal-clad ceramic stove, compared to the wood gas stove that recirculated, might be a big issue. So again, you could do this. How much energy does it take to service? And in the car, about half the energy goes to the gas. But you're not accounting. We weren't accounting for the car itself. How much energy did it take to create that car in the first place? So these, again, questions about accounting and where do you stop? Where do you draw the line of what you're going to be comparing? Depends on what your question is. What do you include? What do you leave out? That's an accounting question, just like it's a systems question. And it really depends, again, on what's the question you're asking. What do you want to do with the analysis? So if we want to compare the energy efficiency of 2 different cars, we can leave out the roads since those are all the same. So again, energy efficiency of cars, leave that out. But we might not be able to leave it out we might not be able to leave out all the different materials that went into making cars. How much does it make to make aluminum versus steel versus plastics, all those sorts of things if the cars had different components. So this is really the introduction to life cycle analysis. We want to account for all the material and energy that goes into a product from the creation all the way to the destruction. And this is a good example of high information demand problems. There's a lot of information in this, and the first step is just to list all the components and processes. And that's as far as we're going to go in this class. But for example, BMWs that are sold in Europe have a code on every part that tells how it should be recycled or sent back to the manufacturer. So this allows this sort of cradle-to-grave recycling of every component of those cars. There's no guesswork, that stuff doesn't get thrown in the wrong bin. It's very interesting. Now, the other thing we're going to come up with in this class is some components and processes that we use, even in very innovative designs, are very well known, but others are novel. Like as we start seeing now new types of batteries being used in electric vehicles. Those are novel chemical batteries that have their own disposal and hazardous signatures and they're all of them, as far as I understand, are a lot better than lead acid batteries. But they're just, there's just new things that we have to learn about, and to do a life cycle analysis of those takes a lot of effort. It's just not something you can look up on Wikipedia. So that's where we are this week. Just this introduction to life cycle analysis, because you're going to be using that when you start talking about your design in the subsequent weeks.